You know, when most of us think about algebra, we think about dusty textbooks, and let's be honest, a lot of confusing rules. But what if I told you that algebra is actually a secret language? It's a tool for telling stories, stories that are hidden in plain sight, inside sets of numbers. Today, we're going to learn how to decode them.
So, let's just dive right in, no messing around. Take a look at this string of numbers. At first glance, it just looks like a random list, right? But I promise you, there is a story in there. There's a very clear pattern. Can you see it yet? Don't worry if you can't. Stick with me, and by the end of this, you'll be able to read these numbers like a book.
You see, every single data set is like a little case file, a mystery waiting to be solved. And today, we're putting on our detective hats. Our mission is to look at the numbers, find the clues, and figure out the story they're trying to tell us.
Now, in any good detective story, you've got to have your usual suspects. Well, in the world of data, these are ours. Each one of these functions has a totally unique personality, a signature move, if you will. Our job as detectives is to match the evidence we find in our case files to one of these culprits.
Okay, let's crack open our first case. This one's a classic, a real open and shut investigation. It's going to show us exactly how to spot our first and simplest suspect.
All right, here's our first piece of evidence, laid out in the table. It's a list of charges from a local pet groomer. On the left, we've got the number of pets being groomed. On the right, the total bill. So, what's the pattern? What's the story here? Let's look for clues. And boom, there it is, the key clue. Look closely. To go from 0 pets to 1 pet, the price jumps by $15. Okay. From 1 pet to 2, another $15. 2 to 3, yep, you guessed it, $15 again. This steady, predictable, step-by-step increase, that is our smoking gun. So, based on that rock-solid evidence, we've identified our suspect. It's the linear function. Its signature move, its calling card, is that constant rate of change. Anytime you see something going up or down by the exact same amount with each step, you know you're dealing with a linear relationship. Case closed. And this is where it all clicks into place. The math tells the story. That equation, f of n equals 15n plus 25, it might look a little intimidating, but it's actually super simple. The 15n part, that's just the $15 you pay for each pet. The plus 25, well, that's the flat fee you pay just for showing up. See, the math isn't just a bunch of symbols, it's literally the groomer's business plan. All right, on to our next case. This one's got a little more drama, a bit of a twist. It's a story that has a major turning point right in the middle. Hey, remember these numbers from the very beginning? Well, this is their case file. The data you see is tracking a patient's heart rate in beats per minute after getting some kind of injection. So, looking at the numbers again, what story are they telling us this time? The key clue here is the shape of the data's journey. The heart rate doesn't just go down and stay down. No, it drops, hits rock bottom at 100 beats per minute, and then it starts climbing right back up, perfectly mirroring the way it came down. That distinctive U-turn is the signature we're looking for. And that U-shape? Well, it only points to one suspect, the quadratic function. Its graph is what we call a parabola, which is just a fancy word for that perfect U-shape. It's the ideal model for any situation that has a clear maximum or minimum point, a peak, or like in our case, a valley. And this is where it gets so cool. The math, that quadratic equation, actually tells us that the lowest point of the curve, the vertex, happens at exactly 10 minutes. And in the real-world story, that's the precise moment the patient's heart rate hit its minimum. The equation isn't just a curve. It's a map of a critical moment in a medical event. It's amazing. Okay, our next case is one where things get out of hand fast. This isn't a story about adding things one by one. This is a story about multiplying. So here's our evidence. A bacteria colony growing in a lab. At hour 0, we start with 2,000 bacteria. 2 hours later, we have 4,000. 2 hours after that, 8,000. Then 16,000. Then 32,000. You can see where this is headed. This thing is blowing up. And that's the key clue right there. We are not adding 2,000 bacteria every 2 hours. That would be linear. No, we are doubling the entire population every 2 hours. The growth isn't steady, it's accelerating like crazy, because the new bacteria are also reproducing. This kind of runaway compounding growth is the unmistakable signature of our third suspect, the exponential function.
It is all about repeated multiplication, which leads to either this kind of explosive growth or, on the flip side, incredibly rapid decay.
So let's just put these two side by side to really see the difference. Linear growth is like getting paid $15 an hour. It's steady, it's predictable, you just add 15 over and over. Exponential growth is like having an investment that doubles in value every single year. The difference is absolutely massive. One is about adding, the other is about multiplying.
So for our final case, we're going to look at something different. Sometimes the most fascinating stories are the ones that actually slow down over time. The pattern here is way more subtle.
This quote really nails the mystery we're trying to solve here. We're looking for a relationship where one number, let's call it x, is just skyrocketing, doubling, quadrupling, but the other number we're measuring, y, just kind of inches along. It barely moves.
Let's look at our evidence. Think about a dog barking. To make the sound feel a little quieter, you have to double your distance. To make it a little quieter again, you have to double your distance again. Now think about the puppies. Doubling the number of puppies doesn't double how long it takes them to get used to a room, it just adds a small fixed amount of time. You see the pattern? In both cases, a huge multiplicative jump in one thing leads to a tiny little additive step in the other. This is a classic case of diminishing returns.
And the signature pattern of diminishing returns points us directly to our final suspect, the logarithmic function. This is the perfect story for things like human perception, sound, light, or learning curves, where you have to put in more and more effort just to get a little bit better. It's the story of things that level off.
And there we have it. We've investigated 4 very different cases, and we've unmasked 4 key suspects. So now let's pull all that intel together into a handy toolkit that you can use out there in the real world. And here it is, your official detective's cheat sheet. So if you spot a pattern of constant addition, your suspect is linear. Think steady progress or fixed fees. If you see a clear U-shaped turn, you're looking at a quadratic. That's a story with a distinct high or low point. If you see that constant multiplication, it's got to be exponential, the signature of anything that compounds. And finally, if you see that pattern of diminishing returns, you've found a logarithmic function, the story of things that slow down and level off. So, we've come full circle. But now you have the tools. You are officially a data detective. You know the usual suspects, and you know their signatures. So, the next time you see a chart online, or a graph in the news, or just a table of numbers anywhere, don't just see the data. Stop and ask yourself, what story is this really trying to tell me?